Good afternoon, my name is Javier Castro, and I will be showcasing my project for Logic Design Lab. For my project, I decided to implement a 2x2-bit binary multiplier. That means that it takes two inputs, input A and input B, each of which has 2 bits, and it outputs a 4-bit number. So the thing about binary multipliers is that if you have a pair of n-bit inputs, the output is always going to be 2n bits. So it's twice the number of bits that each input has. So since the output is going to have 4 bits, we're going to need 4 Karnaugh maps to help us analyze the circuit so that we can then implement it. And if you know your multiplication tables in binary, it's not hard to figure out what each of these K-maps should be, one for each bit. So for the first bit, Z0, the K-map looks like this. And we see that the output is only 1 whenever both A and B are 1. And we can represent this in formula like this. C0 equals A0 times B0. The other bits are a little bit more complicated. For example, bit C1 looks like this. So we need 4 groupings in order to write the sum of products formula. And the sum of product formula looks like this. Luckily, we can factor some things out and end up with a simpler expression. B1 and A0 and A1 NAND B0, and then the other term. So we do this for each bit, and we obtain the formulas, first the sum of product formulas, and then we can simplify whenever possible, and we end up with this. So I went ahead and created a Vivado project, and then here's the source code, the source file, and then I've created a line for each input, A0, A1, B0, B1, and then a line for each output bit, C0, C1, C2, and C3. And then for each of the output bits, I'm computing the formulas that I got on the board earlier. So here we see C0 is equal to A0 and B0. C1 is equal to a more complicated formula, and so is C2. And then for C3, that's a simpler formula, fortunately. It's just the AND of all the bits, all the input bits. And then we can create a simulation file called testbench. And then we use the same definitions as before. Okay? And then I'm going to check all the input combinations. So 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and so on. I'm checking all the input combinations and then checking what the output will be. So here we have the result of the simulation. Let's see how to read this. So I have 8 rows. Each row tells you either an input bit or an output bit. So the first row tells you A0, the second row tells you A1, and so on. We have A0, A1, B0, B1, and then all the outputs, C0, C1, C2, and C3. So the horizontal axis is time. So I'm just checking, across time, I'm just checking all the possible input combinations. So I start with 0, 0, 0, 0, then 0, 0, 0, 1, and so on. And then I'm checking the output to see the result. So we see that when at least one of the inputs is all 0, so here when B is equal to 0, 0, then the output of the simulation is going to be 0. And as soon as both inputs are non-zero, then the output is non-zero as well. So here, in this time frame, B is equal to 0, 1, A is equal to 0, 1, so 1 times 1 is equal to 1. And that's exactly what we find. Here, B is equal to 0, 1, and A is equal to 1, 1. So 1 times 3 is equal to 3, 1, 1, in binary. Okay? And I keep going like this. And the final output we see is b is 1, 1, and a is also 1, 1. So 3 times 3 is equal to 9. 9 is 1, 0, 0, 1 in binary. So we have seen that the simulated circuit behaves just like a regular multiplication circuit. And now that we've seen the simulation, we're ready to implement in the basis board. So I went ahead and created an implementation file, and then copied the code relevant to the basis board that I have. And then I defined several switches, A0, A1, B0, and B1. And then I also created the corresponding outputs, C0, C1, C2, and C3. And then I ran the implementation and generated a bit stream. So since the bit stream has been generated already for the board, we're ready to open the hardware manager and then open the target, auto connect. So I have my board connected to the computer, and now the computer is trying to reach the board. And now that the computer has recognized the board connected to it, I'm ready to program the device. And what this does is copy all the byte code into the board so that I can use it as a multiplier, as a binary multiplier. So here we have the board, and it's completely programmed. And we can flip the first switches, and then we see that nothing happens because we're missing input B. And when we flick input B to be non-zero, we see that the output lights up. So here we have 0, 1 times 1, 1. Well, that's 1 times 3, and the output is 3. If I do 2 times 2, so 1, 0 is 2, 1, 0 is also 2, the result should be 4. And that's exactly what we find. 4 is 1, 0, 0 in binary. And I can keep flicking through the switches. So here I have 1, 0 times 1, 1. That's 2 times 3, which is 6. And then I can do 1, 0, 1, 1, 1, 1. That's 3 times 3. The result should be 9. So this is a completely functional 2-bit by 2-bit multiplier. One of the biggest drawbacks that I had in this project was the way in which I analyzed the circuit. So I used Karnaugh maps. As you can see, they were very useful because they helped us figure out these formulas. But their biggest drawback is that as the circuit gets bigger and bigger, the Karnaugh maps are going to get more and more complicated. So for instance, if I had made a 3-bit by 3-bit multiplier, that means I have 3 bits for each input, and therefore I have 8 possible combinations for each input. So the Karnaugh map for one output bit is going to have 8 rows and 8 columns. Moreover, I'm going to have 6 of those Karnaugh maps because there are 6 output bits. So you see, it gets very complicated very, very quickly. So in order to combat that increase in complexity, real-life multiplier circuits are implemented using rows of full adders. And I will show you now how that works. So let's say you want to multiply these two numbers together. So what you can do is you can create a little table, and then the input A goes here, input B goes here, or vice versa, it doesn't matter. And then for each element of the table, you AND the two inputs. So 1 and 0, that's 0. 1 and 1, that's 1. And you keep going like this. Okay? And once you're done, you can add these diagonally. So you add all the numbers in this diagonal, and the result is 0. You add all the numbers in this diagonal, the result is 1. You add all the numbers in this diagonal, the result is 0. You add all the numbers in this diagonal, the result is 0, 1. You add all the numbers in this diagonal, the result is 1. You add all the numbers in this diagonal, the result is 1. And you add all the numbers in this diagonal, and the result is 1. So in the end, you're going to get 0, 1, 0, 0, 0, 0, 0, 1. We can convert these numbers back to decimal, and we'll see that 13 times 10 is equal to 130. And here we see very clearly that if we have a pair of 4-bit inputs, the output is going to be 8 bits. So we see that hardware multiplication gets more and more difficult the larger the inputs grow. So what many chips will do instead is completely forget about implementing multiplication in hardware, because once you're capable of doing addition, then you can implement multiplication in software, because multiplication is just repeated addition. The main drawback of this is that it's going to be much, much slower. But the circuit is going to be much simpler. Engineering is all about deciding whether the drawbacks that you get are worth the gains that you get. So this has been my project showcase for Logic Design Lab. I hope you enjoyed it.